It's a great pleasure to welcome you all. My name is Kristóf Fenyvesi. I work in the University of Jyväskylä in the Innovative Learning Environments research team of the Finnish Institute for Educational Research. It's a great pleasure to be in Luma ground today, on firm ground of education in practice and also in research. So it's a great day when we have Gabriella Keszthelyi with us as a keynote speaker of the Bring Your Kid to the Workplace, which we had today. So Gabriella already met with several kids of staff people, and I also had the pleasure to be a kid today and explore through coloring and many different games what Gabriella offered throughout the day. So when it comes to the topic of probability, it's highly probable that Gabriella came with a book, and in her hand this is a book what she will introduce us, I think. This been published a few weeks ago, and it's already a bestseller
in science category.
In science category, but it's already have the second print going. So it's really for maths. There is hope for interesting topics. Also, female in mathematics. There are many topics also what we could mention. And the title is something very interesting. I think maybe Gabriella will explain a little bit. Do you want to say something about the title already?
So it can be really translated because it's a pun in Hungarian. Literally, what color is probable? And it sounds like very good in Hungarian is milyen színű a valószínű, so it rhymes. That tells a lot about the whole book. It's like, I think it's very playful. I introduce like lots of stories in mathematics, lots of like paradoxes in statistics and probability, and there is like an arch in the book which is goes through the history of probability. And also one of the main topics in this book is why do we suck at probability, basically? Why are we like really bad at it usually? So that's it, and yeah.
So I come from a family of mathematicians. I've been always the black sheep. I had no too much success in my studies of mathematics, not like Gabi. But I have very good books at home. I get from Osmo Pekkonen, some common friend. So I got this very amazing cartoon comic about statistics. I love it. I learned a lot. Also the mathematics of everyday life, and also mathematical entertaining subjects, magic of mathematics, and also a book of randomness. This whole book is connected to probability in some sense, but all of these books and many other books of mine, I recognize this math popularization book have something written about probability, but not as a full picture as this kind of book. So the floor is yours.
Okay,
Gabi, welcome to the capital of new understandings of probability.
Okay, so thank you everyone for coming. Thank you for having me. And so this wasn't recently, I have to admit, but it's a true story. It was like 2 years ago. I had a dream about a black circular portal open in the sky, and I had to step in the parallel universe. I tend to have these science fiction dreams. And in that time, I was watching a series called The Expanse. I've been watching it for like a couple of weeks. It wasn't like a new series or anything, so it wasn't like a huge probability that I'm going to watch these series around that time. So a week later, after my dream, the same portal appeared without any warning or anything. Nothing was like pointing in the plot in that way. So is this like coincidence, or what's the chance for this. And I will carry on with this kind of topics. So, for example, between 1999 and 2009, the number of films Nicolas Cage appeared in and the number of people who drowned by falling into a pool in the USA showed a strong correlation. I'm not going to tell you yet what is correlation. Maybe I'm not going to tell at all. We will see. But the only thing you need to know about correlation right now, we have like two variables. In this case, the number of Nicolas Cage films and the number of people who drowned into pool, and they tend to move together in a linear fashion. That is basically correlation. And if you look at the figure, it speaks for itself. Like, yeah, they are very similar. So is this a coincidence? Let's start our game. So now if you can open the phone and the QR code which was presented, I have this question: which one is random in your opinion? Is it the left one? Is it the right one? Or none of them? Or maybe both of them? So like most of you voted both of them are random. And the second place is the right one. And that is the correct answer. So the right one is a result of a random process. And yes, you are right. The left one, like too evenly distributed. Right? It doesn't seem like a proper pattern, but I'm going to tell you now that it is not random at all. It is a result of a deterministic process called the Halton process. There are like lots of clusters on the right one. So they are like clumping together the circles. We will see, I hope we will see at the end of this talk, that this is like very natural for randomness. Let's carry on. The second thing I'm going to talk about is it's about the Germans and the World War. So they were the first one who used cruise missiles, the V1 bombs. This is a bombing map. And what you can see on it, that here are some bombs falling very, very close to strategically important places, like the train station. The question is this a coincidence, or they could guide the missiles? So this is the next question. So almost everybody said it can't be a random one, almost everyone. In 1946, there was an English actuary, a mathematician, R.D. Clark, and he took the south of London and just divided into parcels, and then examined in different parcels how many bombs fell. And the question is, does it fit any probability distribution? So this is a lot of new information on one slide, so I will dive into a little bit. So what is a probability distribution? I already talked about it, that when something is random, that doesn't mean that it's evenly distributed. There will be some clustering in the distribution of things. So in this case, it's basically we take the numbers of the V1s which fell into the parcel. There was 237 where there was like 0, 189 where was like 1 bomb, and so on. He just wrote down what were the numbers. And the question was, is this random or not? So to decide what is random, does it fit to any probability distribution? A probability distribution is basically what you see in the middle, that the different numbers has some. So the 0 has some chance, there will be 1 bomb, there is some chance, and so on. And the distribution is that you have a kilogram of sand, and you have to divide these kilograms to the different outcomes. This is what we do here. There are famous distributions. Famous, it means just we gave them a name or somebody actually discovered them. So this one is the Poisson distribution, named after Simeon Denis Poisson. The bombing were random. So Poisson distribution is describing this kind of event. For example, you have a call center, and in every hour you receive, I don't know, 100 calls on average. Then, if you want to ask the questions that in the next half an hour, what's the probability that I will receive more than 10 calls, then the Poisson distribution will give you the answer. What Clark did when he tried to figure out were the bombing random or not, he tried to fit it to some distributions, and Poisson was his best guess. So this is what the middle column says. That's the theoretical numbers by the distribution. And in the third column, you can see what actually happened. And they are very close. There are statistical tests to verify that these numbers fit the Poisson distribution. So at least the southern end of the city, the bombs fell randomly. And here's the gentleman I was talking about. So this is Poisson. The distribution was named after him. How he discovered this distribution is like he was interested in how many times a player would win a game with low odds if they played for a long time. We tend to think that random is either evenly distributed or the lack of pattern, and none of them are true. So random has a pattern, and now we will examine and what is not randomness. Let's go with that. So does it equal to not deterministic? So for example, that the fact that the sun will rise tomorrow is not a random event, right? We are not taking bets for, oh, will the sun rise tomorrow or not? So randomness is definitely not deterministic. So what about predictability? So does randomness equal being not predictable? So the question is, if something is not predictable, does it mean that it's random? That's the question. The example for this, we cannot predict the weather, at least only for like just a few days, but it is not random. Okay, so the weather is very deterministic. The problem is why we can't predict it is because it's a very complex system. It is actually a chaotic system, which is very sensitive for the initial conditions. And that's why we cannot predict it. But it's far from random. So randomness does not equal to not being predictable. What about the iconic coin toss? That's how we always refer to random, right? The best example of being random is we toss a coin and let's see what happens. But I have to tell you, last year, IG Nobel Prize went for a research group which consists of 50 researchers who performed 350,757 experiments, so this many coin tosses, to show that when a coin is flipped, it is slightly more likely to land on the same side as it started. What does this mean? This doesn't mean heads are more probable or tails are more probable or anything like that. It's like it's almost 55% the chance that it's gonna land on the same side where it started. But the explanation for that, this many coin tosses, you develop kind of like a strategy. So it will derive a little bit from random and it's gonna be a bit systematic. But the other thing, so I still didn't answer, like, is coin toss random? Coin toss is also a very deterministic thing, right? If we have a really good camera and a good computer, and let's say that I make a coin toss and I record it with the camera and I don't look, and I just put it on the computer, then the computer, based on the recording, will be able to tell what is the result. of the coin toss. It's not random at all. How is this possible? So the thing is that the coin toss is very similar to the weather. It's also a dynamical system, which is very sensitive for its conditions. And the conditions is the speed, how fast do you toss this coin. The other thing is the angle. Is there some angle? Usually it's not perfectly vertical, so there has to be some angle, which side you are starting from, and so on. Since we don't have the senses to measure these things properly, there is quite a bit of uncertainty in the process. So this is why we call a coin toss random, even though the process itself it's not random at all. Okay, so one more thing about what is randomness. So we already established that it's not deterministic, it doesn't equal with being not predictable, and we said that like a coin toss is random. What is the other feature? It can be explained by causality, like A causes B, then it's not probabilistic, right? Then it means it's a logical connection as well. Like every time when A happens, then B will happen. But it's not this easy either. So these two things, causality and randomness, have a complicated relationship. For example, we like to joke about it in Hungary. The train system is basically always late. You can't really predict how much, and it's like not 100%, but it's 80%. So when you want to get on the train and travel, you have this calculation in your mind. It's usually late. Which train should I get on? So there are lots of probabilities involved, and also some causality as well. Okay, so let's take another example for this. So we already seen the number of Nicolas Cage films and people who drowned in pools. They were strongly correlated. Here's an even stronger correlation. The popularity of the first name Blanca correlates with the robberies in Texas from 98 to 2020. Okay, this is very random, as you would say. Like what is this? So there is this guy called Tyler Vegan. So he has a web page, but also has a book both of them called Spurious Correlations. So the thing is that he just takes lots of database and just compare them in every possible way. Not by hand, of course. He just writes a program to find data which somehow move together. But there is no science behind. Okay, there is nothing behind. He just literally grabs diagrams which look the same and then put them on the same figure. That's what happens. But the correlation is still real. I still haven't told you what is correlation, but I'm not gonna define it. It has a proper definition and you can compute it. This correlation is real. How can these two things go together? So our mind is always looking for causality. Okay, we always wanna hear a story. What's the story behind this? Why do they move together? The popularity of the first name of Blanca and the robberies in Texas. But we can't give you any answers. This is why it's called spurious correlation. But what he also does, he asks AI, and of course, AI gives you an explanation for everything. So let's see what it says. As the popularity of the name Blanca decreased, there were fewer people named Blanca in Texas. That's plausible so far. This led to a significant decline in the formation of all-female heist crews who were notorious for their daring Texas bank robberies. Well, okay. With fewer Blancas participating, the overall violent crime rate in Texas naturally saw a decrease. So my take is correlation is not causation. We thrive for narratives and causations and stories, but sometimes there are just numbers. And what this guy showed, if we have enough data, and we have enough data on the world right now, and you start to randomly compare them, you will find correlation no matter what, even if there is no scientific explanation behind it. And the second is, if you ask AI about it, it will find an explanation for you, even though it's probably not true. You shouldn't believe everything to AI. And let's get back to your point. Here on the picture, you can see the flags of different countries, and on the horizontal axis is the chocolate consumption kilogram per year per capita, and on the vertical axis is Nobel laureates per 10 million people in the population.
Finland is included, as you can see.
Finland is included.
I pointed out.
Yes. It's there. Hungary is not. It's not even on the whatever. But as you can see, in the top right corner there is Switzerland and also Sweden. The correlation is 0.79, which is pretty strong. If you eat like lots of dark chocolate, in the end you will get a Nobel Prize. Okay, so why don't I have a Nobel Prize that like I'm eating like shitload of dark chocolate every day? And okay, come on, people, think a little bit. So this is a confounder case. Yeah, elaborate on that.
More funding, more chocolate, more money.
Yes, that's it. That's the confounder. So the confounder behind it, if you are rich, if your country is rich, you can eat dark chocolate every day, and you can also afford lots of money in science and in research, and you can have more Nobel laureates. Okay, great. We are doing very well. We have seen like lots of patterns so far, and we were always drawn to patterns, starting from the sky to the toast. I don't know if you know this story, but the piece of toast burnt with the image of Virgin Mary sold for $28,000 on eBay in 2004. Do you see Virgin Mary in it? So this is supposed to be the face. This is her mouth, eyes. This is the hair. Yeah, I mean, it's a bit forced. We want to tell apart a pattern is just a random fluctuation. Make enough toasts, then this will happen eventually. Eventually there will be some pattern on it, maybe not Virgin Mary. So let's carry on with that, and I have another question for you. Okay, so let's say that there is a study group at university or in the school or whatever, consists of 25 students, and what is the probability that at least 2 people share the same birthday? Okay, so this is in the poll, so please vote. Just a month and day. And there are like no twins and not thinking about leap years and this kind of stuff, okay? So nobody voted for the right answer. Okay, so the majority said between 0 and 20%. So let's see. This is one of my favorite educational examples because it's a computation, but it's a short computation, okay? So this is called the birthday paradox. Now we are going to do it for 25 people, and then I will talk a little bit more about it. The question was that what's the probability that there are at least 2 people, it can be more as well, it can be like 3 people, was born on the same day and month, not year. So what we will calculate instead here, everybody was born on a different day of the year. Okay, so the first line is all the possible cases. All the possible cases, everybody could have been born on any day of the year. So that's 365 to the power of 25. So that's all the possible cases if we don't restrict anything. If you make this restriction that everybody was born on a different day, then the first person we take, they can born any day, yeah, because it's just the first. The second has to be born on a different day, so they have only 364 possibilities and 363. and we are going down until 341. That's 25 members of the product. And if we take that ratio, these are the favorable cases, this 365 times 364 and so on, and divide it by 364 to the 25, then we will get what's the probability that everybody was born on a different day. And that is the exact opposite what we want, because we want the probability of having at least 2 people were born on the same day. So what we do is we have this ratio and we take minus 1 minus this ratio, and that is 0.57. So the probability of at least 2 people share the same birthday is more than 56%. Okay, the boundary is 23. So at 23 people, it just passes 50% of probability. So for example, my students groups are usually between 30 and 35. And I always do this with them at the beginning of the semester when I teach probability, and we almost always have winners. So there are, in some cases, there's even 2 pairs who were born on the same day. Very counterintuitive. Because when I ask someone, what do you think, like how many people should we collect to get 50%, at least 50% probability that at least 2 people share the same birthday? And they usually say something like 180 something, so around half of the number of the days, the year. And what is the thinking behind it? The thinking behind that is we somehow think that there is this random group or any random group, and somehow the birthdays have to be distributed evenly in any group. And that's just not true. The other question is that, okay, so now we have seen lots of things. We've seen that birthdays come in cluster. We've seen these various correlations. There are lots of data out there, and we want to find meaningful patterns. We want to find relevant information. And how can we find these? Do we have any tools for finding them? The thing is that we've been told, and we are telling this ourselves every day, that we are so rational beings and we are so much better than animals because of this. It gives us the illusion of control. Humans naturally fear uncertainty, and therefore we naturally fear randomness. And this is what makes us really bad at guessing what is random and guessing probabilities. So what do we have instead of that? We have heuristics. So what are heuristics? So when we encounter dense information, like lots of information, usually have a limited time to choose or make some decision, then we use these shortcuts, which is basically just a cognitive bias or a heuristic, and we just grab the first one, what we like. We don't admit this because this is very fast in our head, but we tend to, choose which is somehow familiar to me, which is like, oh, we've seen this before, or something what actually fits our narrative, but not usually the right thing, not what based on the actual information. And let's see another example for that. So here's the story. There is a town and a hit and run occurred in the night. And there was only one eyewitness who saw that a taxi committed the crime. And there are only 2 taxi companies operating that area, the blue taxis and the green taxis. And they are actually blue and green. So the blue taxis make up 15% of the fleet, and the green taxis make up 85% of the fleet. And the eyewitness claims that he has seen a blue taxi. Okay, so what do we do then as prosecutors? The witness is tested under the same visibility conditions because there was a night. So they are testing how how well he can actually see. And the results shows that 80% of cases, the witness correctly identified the color of the taxis. Either way, okay? He identified 80% of the green taxis as green, and he identified 80% of blue taxis as blue. So the question is, what is the probability that the taxi was actually blue if the witness saw blue? And please vote. So who voted between 56 and 80? If you are not shy. Okay. What was your guess based on? Nothing. Just sheer guessing. Okay. So this is the ratio between the blue taxis and the green taxis. Okay, so 50%, 85%. And what happens, eyewitness can't recognize all of them, right? So 20% of them will be falsely recognized. So that means 3 out of the blue taxis will be seen as green, and 17 out of the 85 green gonna be look like blue. So to establish the probability, what we have to do is basically to take a ratio, but the ratio of what? So the ratio of the blue, which actually seen as blue, that is 12, that is on the first 2 column. And what is the 29? The 29 is all of them which seems to be blue. Okay, and that's it. And then the ratio we got is 0.41. So where people usually fail, there are 2 things. Let's go back. So one of them, what is the base rate? And or she was right because she said most of the taxis are green. So that's great observation. Most people just forget that immediately when they hear it. They just discard it. So this is one piece of information. And the second piece of information, how many of them so correctly? So 80%. That looks like a good number, right? 80 is a high number. But when you look at the actual taxis, and there is a huge difference between the ratios, then 20%, which is going to be the false positives, there's still a lot. It will still make a lot up in the green taxis, and that will increase the denominator. Okay, so these 2 numbers decide what will be the probability. Okay, the prevalence of a rare disease is 1 to 10,000. The test used to detect the disease shows false positive in 5%. And to be simple, there is no false negatives. There is always false positive and false negative, but to be simple, there is no false negative in this case. So let's say that you test positive, or someone, not you, someone tests positive, and we don't know about their symptoms or anything else. We just have this piece of information that they tested positive. So what is the probability that they're actually sick? Yeah, let's vote one more time. Okay, so most of you said either between 11 and 50 or between 55 and 80. Okay, so I guess this has to do with the accuracy of the test. It was just 5% of false positives. So let's see what happens actually. So there are 10,000 people. According to the prevalence of this disease, only 1 person will be sick, and their test will be positive because there are no false negatives. But there will be 500 healthy people with a positive test. Actually, it's just 499 and a half, but let's say 500. Okay, because that's the 5% false positive. So what happens then? There are 501 positive tests, but only one of them is actually sick. So it means that if you have a positive test, it's still just 0.2% of the chance that you are actually sick. And this was because it's a very rare disease. So here, the base rate was very, very important. Here, that took away the edge of the effectiveness of the test. So there are two fallacies we mentioned. One is the base rate fallacy, when we forget or fail to take into account the base rate of events, and the representativeness heuristic, which I didn't name yet. So instead of the data, we rely on a specific representative, such as the eyewitness in the hit and run case, or the test in this rare disease. I have one more problem here. So Kristóf, what do you say? Shall we
Ask quick problem.
It's not gonna be quick. I'm sorry. Okay. So suppose that you are at an oral exam and you have to draw one of three topics, and you studied well. You didn't prepare that much. Okay, so you studied one of them very well, and the other two, it's like you are going to fail probably if you choose those. So these are in envelopes and you get to choose. You choose one, and before you can open it, before you can look at it, the professor shows you another one, and it opens it and shows you, and that other one is one of the topics you didn't learn. Okay, so one of the bad topics. And he presents you the choice that you can switch. You can either keep the first envelope, which you don't know what contains the first envelope, or you can switch to the third one, which can still, contain a bad topic or a good topic for you. And this is the last voting. So what would you do? Would you keep the original or switch? Does anyone want to share the switchers? Who wants to switch? Why? Actually, okay, based on real events. Anyone else who wants to share, like, why switch? Because I'm very surprised by this ratio. Usually people want to keep the original. 50, but okay, you mean 50-50 between the two envelopes? Yeah. Then why would you switch? I mean, so you chose one, like you chose this one and here's one. It's 50-50, then why don't you just keep the original if it's 50-50?
There comes some information.
Don't steal my job. Don't steal my show. I want to get there. Don't explain the things. But I think what you are trying to say, and what most people usually try to say, like, oh, in the beginning, it's 1/3, right? It's I have 1/3 chance that I got it. But then the professor who knows, this is very important. The professor knows like what is in the envelope. He didn't just choose like randomly one and shows you. He knows exactly. And let's say that he knows which one you don't know either. So he shows you that here is a bad topic. And we know that whatever we chose first, if it's a bad topic or a good topic, there has to be one more bad topic, right? So it's possible to show a bad topic no matter what was the first one. But what people think at this point, one bad topic is eliminated, then there is one bad topic, one good topic, then it's 50-50 chance. And this is what is not true. So let's see. It's called the Monty Hall paradox. The original problem appeared in an American TV show, Let's Make a Deal, in the 70s. So the player had to choose from 3 doors, which had the following prices. A car was behind one and goats were behind the other 2. So the contestant chose a door, and then the host opened another door showing that there was a goat behind it. And then the player had to decide whether to keep the original choice or switch to the 3rd door. So the thing is, what happens that in the beginning there is 1/3 on the first door and 2/3 the probability that the car is somewhere behind the last 2 doors. And since the host called Monty Hall, actually that's why it's Monty Hall paradox, since Monty knows what's behind the doors, he just shows you not randomly a door, but he shows you a door which behind there is a goat. Then this 2/3 of probability, which originally was on the second and the third door, it just shrinks into the third door. And this is what people usually don't believe, and I can understand because this is very counterintuitive. But the thing is that when you choose a door, like let's stick to the first door, you chose the first door, then you divided the space into two events. It's like either the first door or the second or third door. Those are now inseparable, basically. And what he does, just, okay, I open one door, so this 2/3 of probability has to stay on the third door. We can't really believe it because it's like too few doors. But let's say we have this game with 100 doors. Okay, so there's one car and 99 goats. And what happens that let's say we chose again the first door, and then Monty walks and just opens the doors, like here's a goat, here's a goat, here's a goat, here's a goat. He opens altogether 99 doors and just omits, let's say, the 53rd. And then here's a goat, here's a goat, here's a goat. Would you think that 1% is the chance that I hit the right door? Or maybe it's behind that 53 what he didn't open. Okay, so it's the same thing, and hopefully it's more visible with 100 doors and 99 goats than with 3 doors and 2 goats. But if somebody still doesn't believe it, then I usually say just write a Python code or just ask AI to write a code for you, and then just try it like 1,000 times in the code, just switch every time. And then you will get very clearly in 2/3 of the cases you will win. And like 1/3 you will lose. And okay, I'm really wrapping it up. So what was the cognitive bias we did make? This is Monty, by the way. We thought that we weren't represented by new information. So when Monty opened the door and showed us a goat, we thought, oh, this is no information because, yeah, of course, we know that there has to be a goat besides our door. But this was the main point. This was basically the turning point, and this is what decides on why we have much bigger probability on the last door. Okay, and here is my last take. So pattern and randomness coexist peacefully, and it's us humans who tend to like confuse these two things. Data can exist without deeper meaning. It is us again who seeks a narrative even when there isn't any. And we crave certainty and stories and not probability and randomness. So you probably still don't know what is random and what is probable, but I really hope that you enjoyed this presentation. Okay.
Thank you so much. Do you have definitions for probability?
Yeah, I do have that. Okay. Do you want to hear some? Yeah. So what we do in mathematics, we just avoid to define randomness at all. What we define instead, that there is a so-called thing as random variable, which contains the word random in it, but it still doesn't define randomness, which it basically says that we consider events as sets, as like ordinal mathematical sets, and we like them because we can talk about like intersection of sets, union of sets, and that's very easily translatable to events because the intersection of two sets is two events happen at the same time. Union of sets, at least one of the two events happen, and so on. And the next step, so these are events, this is random events, just sets, And what happens next time that we introduce a measure, a probability measure, which acts on these sets. And that's it. Sorry, this is not that much fun. This is why I didn't talk about it. But we don't talk at all about the metaphysical side of randomness or what is randomness. We just basically introduce axioms and then we just work with those axioms. But the question is fair. It's really new. We also done this around 100 years ago. So before that, we struggled a lot with randomness. We tried to corner it from the metaphysical side, or is it this ratio or the relative frequency, or what is probability? So there were a lot of attempts, but we couldn't axiomatize it, so it didn't work. So it worked partially. It worked for like dices and coins and this kind of stuff, but it didn't work in general. The modern sense of probability, that's it, that events are sets and there is a measure which acts on these sets, that's probability.
Okay. Thank you so much, Gabi. Let's give an applause.
Thank
Thank you.